Welcome to the 61st Theoretical-Physics-Colloquium by Professor Ramona Vogt from Lawrence Livermore National Lab. She received her PhD in 1989 from SUNY at Stony Brook. She had several postdoctoral positions afterwards between 89 and 91 at Lawrence Livermore Lab. Then she was for 2 years at GSI, and she became a staff scientist at Lawrence Berkeley Lab between 93 and 2007. The last 14 years, since 2007, she is a staff scientist at Lawrence Livermore National Lab. And she's also an adjunct professor at the University of California at Davis. Over the years, she received many honors, including a Rosenberg Fellowship from Niels Bohr Institute. She was honored as a Kaskaskia College Alumnus of the Year in 2001. In 2001, also, she had UC Davis Academic Federation Excellence in Research Award. She was elected a Fellow of the American Physical Society from the Division of Nuclear Physics in 2010, and she received another honor as an outstanding referee from the American Physical Society journals in 2017. She is very active in the professional service. She served in many capacities at the American Physical Society. In 2008, elected member at large of APS Topical Group of Hadronic Physics, later elected chair, 4-year term, going through vice chair and past chair. She served on editorial board of Physical Review C, Physical Review Research. Actually, she is serving now on Physical Review Research editorial board. She served as an elected secretary treasurer for many years, actually, at a group of hadronic physics, as well as DNP, Division of Nuclear Physics, and in many other capacities that I will not mention here in detail. Her research interests include phenomenology of nuclear fission, heavy flavor physics, charm boson quark productions, quark-anion production in proton-proton, proton-nuclear, nuclear-nuclei collisions. She is an expert in quark-anion production and suppression, dilepton production, properties of quark-gluon plasma, signatures of quark-gluon plasma, and many other things in low and high energy nuclear physics. So today she will be talking about new developments in spin physics in relativistic heavy ion collisions. And with that, I'll give the microphone to Ramona.
Well, thank you for that very extensive introduction. So I'm going to be talking about heavy flavor kinematic correlations, starting off in proton-proton and then going on to cold and hot nuclear matter, more or less schematically. So here we go. So first I'll talk about some motivation and then heavy flavor production, and then for single inclusive, and then go on to heavy flavor pairs, talking about some of the effects of fragmentation and broadening on pair production, and then comparing CC bar and BB bar correlations to collider data, and then looking at nuclear matter effects, starting with single distributions and then on the pairs. So there's a lot of information that you can get from single inclusive measurements, but there are very many models in medium production and modification, and some of these have trouble describing both low and high PT simultaneously, and so that's why we want to consider correlations. So, for example, there are several collaborative projects that have been going on to study the similarities and differences between a lot of these medium models of heavy flavor production and transport. These are a couple of papers from a couple of years ago, and I know that they're continuing to work in this direction. But these models have different approaches to both the initial, say, heavy flavor distributions, some of them use the F1LL or zero mass variable flavor number scheme. Others use power law fits to the initial distributions. Some use leading order calculations with some partial next to leading order supplement. Some use Pythia, tuned to match results from PQCD, and there's a wide range. And then heavy quark hadronization. There sometimes these are considered to depend on the bulk evolution, and other times not. Some use the F1LL fragmentation functions. Others use the Peterson fragmentation function. Some use PP inspired or E plus E minus fragmentation functions, and some use some kind of in medium approach, such as regeneration, coalescence, recombination, or some or all of the above. And some include nuclear modifications of the parton densities. And if you don't include it in the initial calculations, but instead use like a power law fit, then you really can't include shadowing appropriately because you don't know the x and q squared values that you would need to input. So those are just those two things I've just mentioned are really to do with the heavy flavor production itself, but then you also have to worry about the transport and bulk evolution of the system. So I mean there are many different paths to go, and this is only like a few of the models that are shown here. I would suggest that if you want to look at more, you should go back and look at the references on the previous slide. So at low PT, the results are supposed to really reflect the collective motion of the system or thermalization. And at higher PT, because the heavy hadrons will spend less time in the medium, they're going to be more susceptible to things like energy loss. So here are two classic measurements of heavy flavor and RAA, which is the nuclear modification factor. It's the ratio of per collision of the cross section in AA relative to PP at the same energy. A lot of times they've been measured at the same energy, but not always. And sometimes the PP baseline, at least experimentally, is not as good as the AA. And then here we also have the elliptic flow V2, which is related to the initial spatial anisotropy of the system. So it'll tell you something about the anisotropy of particle emission. And that's usually shown at measured at fairly low PT. So you can see that models that get RAA right in some region may not also describe the V2 in the same region in PT, but there's a wide range of low PT. At high PT, there's it's not there's a lot of things that a lot of models that don't do well in one but do well in the other, and vice versa. And so there's a lot that you still need to learn, but you need a little bit more than just these single observables. And clearly, in these collisions and heavy ion collisions, the mass makes a difference. We talked about the dead cone effect. So there's a hierarchy of suppression that's based on the quark mass. So here's RAA as a function of PT from 1 GeV up to several hundred GeV, measured in different from CMS with different particles. So the yellow are charged hadrons measured over the biggest range of PT. And you can see that the D mesons are less suppressed at lower PT, but then they get to be similarly suppressed as the charged hadrons. And then for B mesons, you see that the same thing. These are actual B mesons, and here's the B's from non-prompt shaped size. So you can see there is a similar trend. You see there's less suppression for heavier quarks, but then as you go to high enough PT, you see a similar suppression for all three. and that's because when the PT gets much larger than the mass, then the the heavy flavor is essentially light as well. And you can see for one particular calculation here, the ratio of C to B energy loss compared to data, the ratio of RAA for charm to bottom. And you can see here that from these atlas results that there is a suppression at high PT for charm relative to bottom. All right, so I want to go back to more elementary collisions, PP and PA, to look at what we know about heavy flavor and correlations, especially because they're more complex observables. And of course, naively, at leading order, the pairs are produced back to back. But at next to leading order, there are contributions that can change that correlation. And we'd like to know like how sensitive it is to the PT cut, the ingredients of the model, and so on, and then apply that to see what changes in correlations you might expect in heavy ion collisions. So as far as production and decay of these QQ bar pairs goes, these figures here, A and B, these were made by Andrei Mishkin in Physics Letters B from some time ago. But see, in both cases, here the initial QQ bar pair then hadronizes. Here CC bar goes to D0, D0 bar, and then they both decay, and you can look at, let's say, reconstructed Ds. You can look at the lepton correlations, for example. For BB bar, it gets a little bit more complicated, but because you have an intermediate D or they decay to a J psi, and then you can measure these types of correlations. In fact, the LHCb collaboration is measured B goes to J psi, so J psi pair correlations at 7 and 8 TeV that I'll talk about. And so you see that there are many different ways of putting together correlations from these production. So at leading order, one has only QQ bar and gluon, but at next to leading order, there's this new channel, QQ bar plus gluon. And if you look only at, if you only look at, say, an event generator like Pythia, you will get something different because, I mean, in PQCD, the correlation, the contributions to production get sorted by the initial state. So you have all the GG contributions. These first three diagrams would all be, one part added all up together. But in terms of an event generator like Pythia, these diagrams are split up based on diagram topology. So here you have like two QQ bar in the final state, Q and a Q bar, sorry, in the final state. Here you have, say, 1, and here you'd say 0 because you start with the gluon before it splits. And so Pythia has labels like flavor creation, flavor excitation, and gluon splitting. And so when those labels are for the event topology, not any production mechanism, although I've seen people take it that, okay, so gluon splitting, that's a new production mechanism for heavy flavor. And that's not really the case. That's part of the GG contribution to the total production. And all of these get added up, and their amplitudes are summed and squared, which is not possible when you do these calculations with event generators. It will eliminate the interference, and you don't have then the right total cross section. And what some I've seen from some experimentalists, they use Pythia to sort of reweight all these different contributions to try and say, okay, this much here we have, I mean, is all due to this particular mechanism of gluon splitting or flavor excitation or whatever. And that's not really how QCD works. So I want to try to to look at the data in terms of just straight QCD, and see if it's adequate according to what the data is telling us. So to calculate heavy flavors in PQCD, we know we have a hard scale in the calculation that makes it applicable, and we can calculate the total cross-section assuming collinear factorization based on the parton densities in the proton or for nuclei, and those are determined from global analyses, both for protons and for nuclei. And in nuclei, they're getting more and more sophisticated. And then you have the proton momentum fractions carried by the partons, and then the hard protonic cross section. So I mean this we can calculate, and the energy dependence of the total cross section depends very strongly on the factorization scale that's chosen. So then going to schematic a single inclusive heavy flavor production, you have the quark production that's calculated in perturbative QCD, and then you have the hadronization, however it's done, and then the decay to the final state. And if you're looking at reconstructed D mesons or B mesons, for example, then you can skip this decay part. And both of these results, and also for the empirical results, depend on the quark mass and the factorization scale and the renormalization scale. And for fixed order and excluding log and the zero mass variable flavor number schemes, the heavy quark is treated at light for large PT over M, and there's a matching of the massive and massless parts. And they're treated slightly differently in both cases. So to calculate the theoretical uncertainties on the cross sections, what we've done is to take for the charm quark mass 1.27 GeV and 4.65 for the bottom quark mass, and then we fit the total cross sections and vary the scales independently within 1 sigma of the fitted cross section. So for charm production, the factorization scale is mu f over mt is 2.1 plus or minus 2.5 and plus 2.5 and minus and nearly 1, and 1.6 plus or minus about 0.1. And for bottom production, it's mu f over mt, and mu r over mt is closer to, say, 1.4 and 1.1 with smaller uncertainties. And the uncertainty band on a cross-section that you see, whether it's a distribution or the total cross-section, it comes from the upper and lower limits of the mass and the scale uncertainties added in quadrature. And actually the mass is a much larger contribution to the uncertainty than the scale itself, typically, except say for low factorization scales in PT distribution. But the theoretical uncertainties can be large. So here is an example of the total cross-section calculation for CC bar as a function of center of mass energy on the left, and for BB bar on the right. There's a tighter fit for BB bar, but the cross-section data are slightly more, fluctuate somewhat more. You can see that using this kind of fitting actually reduces the uncertainty band significantly, and even though we didn't include the LHC data in the fit, it agrees very well with the central value. So as far as single inclusive results go, this is a Alice measurement here at 7 TeV. I think they're all Alice data from central rapidity, and this is here it's compared to F1LL, the generalized mass variable flavor number scheme, and leading order KT factorization, and they all can sort of explain the data on the log scale, but if you look at the ratio as a function of PT, so the data to the calculation, then both F1L and the KT factorized are somewhat above 1. The generalized mass variable flavor number scheme is a little bit below, but it starts at somewhat higher PT. Some of the KT factorized results that are shown here in the bottom right for different unintegrated gluon distributions tend to be a little bit low here as well. And then the blue is a calculation that we did based on the mass and scales values determined from the fit. And this is the F1LL result. As you can see, it's fairly low and that's using, of course, MC of 1.5 and varying the scales by a factor of 2. So the result down here at low PT is the fact that you're getting into where the PT is lower than the factorization scale at some point. And that's for mu f over mu f of a half, actually. Okay, so now we want to go to production of correlated QQ bar pairs. And I already mentioned that there's different levels of exclusivity. So total cross-section, all the momenta are integrated away. For single inclusive, you keep only the momentum of one quark or antiquark. And for exclusive pair production, you keep the momenta of all the final state partons. And so these exclusive calculations are needed for correlation, so you can't actually use F1LL since it's a single inclusive calculation. There are a couple of general approaches. HVQ MNR is a fairly old code. It has no resummation, and it has some problems at high, in cases where PT goes to 0 for pair production, and it uses Peterson function as the default fragmentation scheme. POHEG is typically interfaced with a parton shower Monte Carlo, and so I wanted to avoid that. So I'm using the HVQ-MNR code to calculate the correlations, but the fragmentation and KT broadening that's used to eliminate these divergences at low PT are adjusted to reproduce the F1LL PT distributions on for the single observables, and I'm going to show that in a minute. So how do I implement these fragmentation calculations? So F1LL uses different fragmentation schemes for charm and bottom. The charm quark results are calculation that are based on Mellon moments compared to E plus E minus data, which is the similar approach to the Peterson fragmentation function, which is originally fit to E plus E minus. So for D mesons, they use a combination of pseudo scalar and vector fragmentation for ground state D mesons and then D star. And the average value of Z for the sum of those two contributions is about 0.8. And so that means that about 80% of the charm quark momentum is carried by the D meson. And for bottom quarks, they use a polynomial fit, Z times 1 minus Z to the power epsilon, where epsilon is about 27 for a mass of 4.65 GeV, and this gives an average Z of about 0.93. So most of the B quark momentum is carried by the B hadron. Now, HVQ-MNR employs this Peterson function for...
yeah, the question here, talk about charm mesons, but not charm baryons.
Yes, and that's because all of the measurements that I'm going to show comparison to are with the D mesons. And there's no good fragmentation function that I have found for charm baryons. at this point. You have to, something else is used sometimes. But charm baryons are a little bit harder to calculate because of that. Does that answer your question? Okay. So the HVQM&R is using the Peterson function for fragmentation, and this is the Peterson function here, and it has one parameter, this epsilon p, for both charm and bottom, and the standard value for me plus E minus is 0.06 for charm and 0.006 for bottom, giving an average Z of 0.67 for charm and 0.82 for bottom. So for B quarks, actually, the average Z is similar to what the charm quarks are for F1LL. So to match these results at high PT with KT broadening, which is effective more at low PT, then you need to reduce this epsilon parameter to about 0.008 for charm and 0.0004 for bottom to get about Z of 0.82 and 0.93 for charm and bottom. So the red is in both cases here is the default Peterson parameter, and the blue lines are the results for F1LL for the total here for vector plus pseudoscalar, and then the this polynomial on the other hand for bottom, and then the black curves show basically what the Peterson function looks like with the adjusted parameters. So it's not exactly the same, but the average Z is the same. So now in terms of KT broadening, it's absolutely needed for pair production, and even though it's not included in F1LL, which includes only fragmentation, not broadening, it is used in this the HVQM&R code because, like I said, of the fact that you have for the pair distributions, you need something to tame the behavior as PT goes to 0, but also interestingly enough, when they first developed this code, they were looking at mostly fixed target data, and when you include the standard Peterson function with the default parameters that I mentioned, it reduced the average PT at fixed target energies so much that they really had to include KT broadening to make up the difference in the distribution and match the data. I mean, it's not unheard of. It was done already for de Rallian production to make the low PT distribution finite, and it's a way to take the place of a full resummation calculation. And it's usually applied in many cases in the initial state. In the code, the way it's done is to apply it in the final state because of ease of implementation. And if the initial state PT kick is not too big, the KT squared between say 2 and 3 GeV squared, then it should be equivalent. And I include an energy dependence of this broadening. In their original results, they only used 1 GeV squared, but they were applying only to fixed target energies for very low energies, say 20 GeV or below. So this is the energy dependence that we use with this n here fixed from calculations of J psi and upsilon PT distributions in the same code but with a mass cut. So n equals 12 for charm and 3 for bottom. So now you can see how using the HVQM&R code, how the single inclusive PT distributions depend on the KT broadening and the epsilon parameter for the fragmentation. So the solid blue curves for charm and bottom here are just for the charm quark distributions and bottom quark distributions. When you add the default Peterson function, you'll go from the solid blue curve here to the dashed one. So it's a huge difference in the slope of the PT distribution. And you have to decrease this parameter to get anywhere close to what is needed for the to describe the data. And in fact, in a lot of cases, the F1L distribution is not that different from the single quark distributions. So you can see that KT broadening doesn't make a lot of difference in the results. It's a difference between here the red line, which at 7 TeV, this average KT squared is about 1.5. If you double that, then you go from the red curve to the magenta dash curve. There's not much difference, and the differences are even smaller for the B quark distributions and B meson, actually, I should say. So then, if you compare these PT distributions to F1L and to the data, you see they're almost exactly on top of each other for this LHCb D0 measurement. This is in forward rapidity. This is one of the bins that they had data for from LHCb. And so there's a good match here, and there's also a quite good match for B mesons measured by Atlas. HB is their way of saying it's a heavy, bottom hadron. So they're quite good in agreement with each other and with the data also for this Atlas measurement. And this is at central rapidity. So based on this, then I go ahead and do the calculations for the correlations at LHC energies. And so I want to look at the fragmentation and broadening effects on the delta phi distributions, or the difference in azimuthal angle between the opening angle between the C and C bar, or the B and B bar. And you can see that changing the fragmentation function really has very little effect on this correlation in both cases. But as soon as you give it a KT kick, for charm especially, you see a big difference. The peak is just reduced here for bottom, but for charm, you're basically going from a back-to-back correlation to something that's more similar to slightly peak at 0 degrees or more isotropic altogether. And that's because a kick of about a 1.5 GeV squared is not that different from the charm quark mass itself. And so you can easily decorrelate it and get something more isotropic, whereas the B meson mass is still significantly higher than a KT squared kick of 3 GeV squared. So you see that the broadening has a big effect on charm and also on bottom, but not as large, and also that the fragmentation doesn't have a very large effect. And in both cases, generally, without broadening, you have a back-to-back peak. And of course, since this is next to leading order, it also includes the fact that you have other, you have a third parton in the final state for real emission at next to leading order, and that's why you have this tail instead of a delta function. So now I want to look at the sensitivity of the results to the KT broadening and also the PT cut. So for charm, for both cases, I basically went from 0 to the default value that was shown in the previous slides in the red curves. And so that means I'm going from -3/2 to 1 for charm and -1/2 to 1 for bottom. And then I'm going to look at the sensitivity as well to the general PT cut of less than 10 GeV and greater than 10 GeV. And we'll see that the effect is independent of rapidity, so it really doesn't matter which rapidity range I'm showing here. So for charm pairs, for PT less than 10 GeV, you see, that it's not, this huge effect we saw from going between 0 and 1 in delta isn't, it does show a more gradual turn on. So it goes from, say, this delta of -3/2 is for a KT squared of about 0.25 Jev squared. So even a small kick will start making it more isotropic, and it just goes, the peak goes down a little by little on closer to back in this case, and you can see that if you look at the ratio for a different KT squared to KT squared of 0, and you see that there's a trend that it's about delta phi of about 1 radian, where you see that all the curves are crossing each other. Whereas now for PT greater than 10 GeV, all that KT broadening effect has gone away altogether. You can look at the ratio and see slight difference at close to back, but you can barely make it out here, but you can see it a little better in the ratio. So in PT greater than 10 is a huge cut, because it's already a factor of several times the charm quark mass. Whereas for bottom, you also see a more gradual turn on once you've gone above, say, this -1/2 means it's just slightly above 0, and then here this is like 1, 2, and 3. So it is for GeV squared. So it is a bigger. You can see that it's a smaller effect than for charm, but it's still significant. And then here you see the ratio relative to KT squared of 0, and here that turn in the ratio where the curves all cross is at about 2 delta phi instead of 1. So that makes a difference in the mass as well. And then because the bottom quark mass is still maybe half of PT of 10 GeV, then you see there's still an effect that's kind of visible in the BB bar as a function of delta phi, whereas you didn't see that at all for charm. If you go to, you would have to, for that effect, you would have to go to PT of, say, maybe 20 GeV. So now I want to start doing some comparison to data. So LHCb measured these charm pair correlations at forward rapidity, and they actually measured CC as like D plus, and CC bar like D plus, D minus. And the CC is over here on the left, and CC bar on the right, and you can see a big difference between the two. So, and also there's a big difference in the statistics. There's about 10 times more events here than there are for the charm, and these you can see that the CC are more isotropic in the delta phi, and it's not shown, but the pair PT distributions are harder, and so these CC events are likely came about by double parton scattering, so 2 CC bars in the same event, whereas these are definitely coming from a single CC bar in the event. And as you can see, this looks fairly characteristic compared to what I showed for a higher PT cut before for CC bar, where you see a forward peak. Sorry, a peak at around 0 degrees. So now I can compare these two delta phi distributions that were measured by CDF at 1.96 TeV, and here the D and the D0 and D star minus are measured for PT greater than 5.5 GeV and 7 GeV for D plus, and you can see the results agree quite well with the calculations. And here is compared to the LHCb with results for PT greater than 3 GeV for the DD bar pairs. It's not quite as good at very high delta phi. So, but the peak is definitely coming down and is in reasonably good agreement with most of the distribution. So now this is delta phi divided by pi as opposed to just delta phi that was shown here and on the previous slides. So LHCb also measured the CC bar pair mass and the difference in rapidity, and so you can see that the mass distributions are in good agreement with the calculations, except for those where this delta is 0 or where KT squared is 0 or deltas are fairly small. So it agrees quite well with the default KT kick actually for the mass distribution and also for the delta and Y distributions. And here you can see that all of the curves are basically on top of each other, so that the rapidity distributions, as I said, are not changed. So now we can look at the LHCb BB bar goes to J psi pairs. Now they put together their data from 7 and 8 TeV so that they had higher statistics, but then they also just showed the cross section, the log of the cross section, so that those two data sets are in good agreement. And also when you do that calculationally, you see that there's no difference for the shape of the distributions from 7 and 8 TeV. So they had 6 pair observables that they mentioned. I'm not going to show all of them here. I have some in sort of backup, but they looked at the delta phi distribution between the B and B bar and also the opening angle between the two J psis. And then they looked at the pseudo rapidity difference between B and B bar and between the J psis. They also looked at the PT asymmetry between the J psis, the J psi pair mass, pair transverse momentum, and rapidity. And for each one, they looked at different PT cuts, PT greater than 2, 3, 5, and 7 GeV. So that's a little bit finer graining than I showed with my PT less than 10 and greater than 10, but it should show some difference in these distributions. And so all these observables are calculated in my calculations for the BB bar and the J psi pair decays. So here's the delta phi over pi and the log of the cross sections. The black data points are BB bar and the red are J psi. You can see there's not much difference between the data sets in the two cases. But you can see there's a big change in the distributions for, these are all assuming the default value of the KT broadening. And you can see that the BB bar is a little bit higher at delta phi over pi is close to 1, and it's more isotropic, at least for PT greater than 2 GeV for the J psi pairs. But as you go higher in PT, you see that the shape of the distribution changes significantly. You get away from more isotropic and more of a peak back to back and at 0 degrees. So that difference that we saw between almost for BB bar of almost isotropic to something that's peaked at 0 and 180 degrees, you can see it developing here as you go up in PT from 2, 3, 5, and 7 GeV. On the other hand, this delta Y distribution doesn't really change either for the data or for the calculations as a function of the PT cut. So and it doesn't change between BB bar and the J-psi pairs. So that's actually interesting and reassuring. In fact, that I had said that it should not depend on delta Y. These are the pair mass distributions. And the J-psi pair, you can see, is in very good agreement with the calculations altogether. And now these are the pair rapidity distributions. And again, there's really very little difference between the BB bar and J-psi. And also there's not much change as a function of PT. It goes, the peak and the pair rapidity is reduced somewhat as you go to higher PT, but there's not much effect on the hadronization. And I want to go back just one quickly here and say that the correlation gets kind of wiped out for the J-psi. So when you look at, if you look at this as a function of the KT kick, for example, if you go to 0 KT for J-psi, you don't actually see this big peak that you would expect, because the fact that the decays to the J-psi is more isotropically, then it would reduce that the dependence on KT altogether. So now I want to switch gears a little bit and talk about nuclear matter effects in PA. So we can look at cold and hot matter effects on the charm RP lead, and these are, say, cold matter calculations where this is the red curves are PQCD calculated with shadowing and only, and then we have it's an incoherent multiple scattering. This is a CGC calculation, and then the green curve has kind of power corrections and cold nuclear matter energy loss. On the other hand, you can also do a hot matter calculation with the Polang generator for hard thermal loops and perturbative QCD. You can see a big difference between them. And then Duke is a multiple scattering calculation and multiple scattering in matter. So my calculation here is with EPS09 and also with difference in the KT kick. There's not much difference between 0 and 1.5 GeV squared. You see a slight difference when you go to a doubling of the KT kick for PA compared to PP, but it's not very significant. And here we have the cold nuclear matter effects on single bottom PT distributions. These are compared to non-prompt J-psi and B+ as measured by LHCb. And here is what one might expect for lead-lead with the EPS09, and then this is a KT kick of 4 times the that in PA, sorry, in PP. A factor of 2 more for PA, and then for the second nucleus, adding another kick. And you can see it does change, it changes the slope of the R lead. So now I can look at the nuclear matter effects on pair observables. So we studied the BB bar pair observables with different PT cuts to look at hot and cold matter effects. So we introduced additional broadening for due to chronon in proton nucleus and nucleus nucleus, and to simulate energy loss, we changed the Peterson fragmentation parameter back to its default value to try and look at the effect in AA. And so this is in BB bar. We'd see even larger effects in CC bar because the mass is lower. So we included the nuclear modification of the parton densities. And here, this shadowing factor gets multiplied by the proton parton distribution, and the chronon effect is modeled by in PA, making delta here 2 instead of 1, and in AA making it 4. And then the fragmentation parameter is increased to be the value in E plus E minus in AA collision. So that's a huge effect, but I'm just trying to illustrate what the effects on the correlations might be. So now, as I mentioned, I'm showing several calculations here, shadowing plus additional broadening in PA, and shadowing plus additional broadening, but a larger broadening in AA, and also increase the fragmentation parameter. And the proton nucleus results are calculated at 1.816 TeV, which is the measurement that's been done most recently at the LHC, and in AA at 5 TeV. And the PP is calculated at the same energies. I'm showing results only here for forward rapidities, where you would have, say, a higher effect due to nuclear shadowing, but the dependence is similar for central rapidity. So you can look at the paper and see more details on that because both are shown there. And then I looked at the delta phi and the pair rapidity. And the results for the pair rapidities are more sensitive to the changes in the fragmentation function, while the azimuthal effects are more more sensitive, to enhanced KT broadening. And I looked at different PT cuts, the same ones that they used for the BB bar goes to J psi pairs, 2, 3, 5, and 7 GeV. So first I want to look at the distributions themselves to see how the changes look on the shape of the cross section. So these are all different energies, but say the difference between 7 TeV PP and 8.16 TeV for proton lead are negligible here for the pair rapidity distribution. It's only when you change the fragmentation function that you see there's a shift slightly backwards in lead due to that change. And you can see it's even bigger effect for PT greater than 7 GeV. And you can think about that just by remembering what I showed for the single inclusive distributions. When you have a change in the fragmentation function, then you have a steeper, more steeply falling PT distribution, and that's why you have a bigger effect here at higher PT than at lower PT. And then you can look at the our P-lead at the top and our lead at the bottom, and you see here for the different PT cuts, there's almost no change as a function of either PT or rapidity. It's fairly flat altogether. But when you go to lead, you see a slight difference as a function of rapidity based on the PT, and that's because you have nucleus in both directions. So that's this is mostly due to shadowing here. I mean, this is all due to shadowing, sorry. And then this is the effect due to the KT kick and the change in the fragmentation function, even though I don't have it on the plot, sorry. So you go from something that's fairly flat for PT greater than 2 GeV to stronger suppression at PT greater than 7 GeV. And this is all due to the fragmentation. It's not because of the KT kick, as you could see from previous calculations. So now we can look at the energy and matter dependence at delta phi, and here they're not the same because the KT kick is different in all three calculations. So in the PP, you see this fairly characteristic result that I showed earlier as well, but it gets a little bit reduced. The back-to-back peak gets reduced and it gets slightly more isotropic as you go from PP to PLED to lead-lead, because this default value of, this value of delta is going from 1 to 2 to 4. And you can see it here somewhat more strongly in the pair distributions for PT greater than 7 GeV. So it's clearly dominated by the KT broadening and not anything to do with the fragmentation, as it was already shown by some of the previous calculations. So here with shadowing alone and proton lead and lead, you see there's not much of a effect on the PT on these delta phi distributions, the function of PT cut, or on the by the energy or anything else. But here on the right, you can see that the point where the slope starts to change from being flat to decreasing as you go to delta phi close to pi gets higher higher and higher from PT greater than 2 to PT greater than 7, and you see that effect also on for lead, but there's a little bit of a shift here also due to the that may be due to the fragmentation, and so this you can recall by looking at the ratio of these delta K the KT distributions. I mean for different KT. Sorry. Okay, so you can see that there's that there these two different measured observables are very sensitive to different aspects of modifications. So they depend differently on the hot and cold matter effects. So the pair rapidity is sensitive to the energy loss, and the azimuthal separation is more sensitive to, say, PT broadening effects. But on the whole, these heavy quark pair observables, while they may be harder to measure in nucleus-nucleus, they could provide more constraints on models and somewhat more detailed information. And these pair correlations in PP and PP bar can be explained by the next leading order calculation production processes without having to revert to different topologies of diagrams. And PP is most sensitive to the KT broadening at low PT, but they're not very sensitive to fragmentation and hadronization. You see more sensitivity when you go to hot matter effects. And that's all I have. So thank you very much, Igor, and I'll take any more questions.
Thank you very much for a nice presentation. Now let's have some questions. So if you do have a question, please raise the hand or let me know in any other way that you have a question. While people are thinking, I had a question of my own, so let me see that I see it. Right. So I'm actually mostly interested in the effects of the medium, like cold or hot, well, primarily hot, let's say, medium in heavy ion collisions on these correlations. So what you seem to say, and correct me if I misunderstand it, that even in PP collisions, there are still some modal dependencies that we may need to sort out. So with all of that baggage, when we are coming to the heavy ion collisions, how reliably we can say extract the properties of the actual hot medium from this production, from heavy flavor productions?
Well, I would say that yeah, it is difficult, but I mean, especially because the pairs are hard to measure in media as well. But I would say that whatever model they use for the transport, they should know. They should also, try to first, show that they can get the distribution right for single particles. At least, I mean, not just the RAA, but show the say PT distribution and proton collisions, and that they can reproduce that, and then the correlation that's already been measured in proton, and then
Right. So
and then go on to see what they can say about.
Right. So I absolutely agree that first you have to sort out your model so that you have the starting point, right?
Right.
And it's sort of absolutely fair statement, but maybe the aspect that I wanted to fish out of you is basically something a little simpler. Since you have experience in these models and basically from all the aspects, the question is, which of the potential observables of matter you think are most promising to be fished out of this information?
So I mean, I think you can, the the biggest change from my calculation seems to be the change at lower PT due to the broadening effect. In the delta phi distributions. So that could be interesting to look at, and you can get some idea of how big that change is just by looking at the shape of that distribution relative to PP. And
Right.
providing that PT cut gives you more information as well. So, I mean, if you would see no difference, say in that delta phi distribution, then in lead relative to proton, then there isn't any bigger broadening effect. It's not a PP broadening plus, it's just the PP broadening. So it's the same level, whether it's proton or nucleus. The energy loss and the rapidity, pair rapidity distributions is a little more subtle. It isn't quite as big, but that could provide some additional information also. I mean, and the fact that it isn't as big is kind of amazing because the Peterson parameter that I used changed by more than a factor of 10. And you won't see any that energy loss won't show up in the same, if it's kind of like this change in the fragmentation, which does change the PT distribution significantly. I mean, if you go back and look at the here, say for for charm and bottom. I mean, just going from B quarks here to B mesons with that Peterson function, and even going between that with the default value that I used for Peterson function and the actual Peterson parameter, you see a change in the slope that's significant here and here, but it has no effect at all on the I mean, almost no effect at all on the azimuthal distributions, just on the pair rapidity or pair PT. You would see that on the pair PT distributions as well.
Right. Okay. We have another question from Graziano Mileta. Go ahead.
Okay, thank you for your talk. I have this question. BB bar or CB bar pairs can produce the photons at high TV energies via J-psi. I mean, since the photoproduction process does not satisfy the so-called anomalous triangle singularity condition, the presence of BB bar or CC bar at these energies could produce the photons, and these the photons, which as real as highlighted on Physical Review letter published on July 2019, could they produce lepton pairs? Do you think it could be a lepton production channel?
I had a little bit trouble understanding completely the question. Sorry, but you're asking if
my question is this: BB bar or CB bar pairs can produce the photons, photons, real photons.
Yeah. So you're asking if the pairs would then, what happened if the pair would radiate high PT photons?
I suppose that's the question.
Yes.
Okay. Yeah. So, yeah, that, of course, if they radiate photons, then yes, it could change the distribution as well. We could change the pair observables, but also change the single particle observables too. But I would say, I mean, I think it would be a slightly, I mean, this would happen less often probably because you have than say radiating a gluon, which would, they would also contribute to energy loss, but in a different way, and because the photon emission is by alpha instead of alpha s, it would be down by an order of magnitude probably in the coupling, and so it would be less probability for that than say gluon emission.
Okay. Are there any other questions?
Thank you.
Are there any other questions? Actually, since you are on this slide, I sort of had some minor question about this left figure.
Yeah.
So essentially, if I'm reading it right, you're saying that KT broadening of 1.5 and 3 GeV is essentially going to shape dramatically the whole shape of this distribution to the point that it's not even flat, but with a peak at phi 0. Isn't that a bit puzzling? Why does it have to peak at phi equals 0?
Well, I mean, okay, there are several reasons for that, and say first, like I said, at leading order, there, it's just a delta function here at pi, basically. And now when you introduce a next to leading order, you can have you know, a light parton emitted somewhere in the final state. And that would tend to make things more isotropic, but you know, less, not very strongly so. So that's why you have this tail here. But now, and you introduce this KT kick, you see that okay, this is the default value here in red, and my default value. So that's, as I said, that, you know, KT is about 1.25. The charm quark mass is 1.27. So you have some, you know, you're kicking the quark with about as much energy as its mass.
Then
So,
it should be isotropic, not
yeah, it should
peaking
be,
at zero. That's my question. Why is it peaking at zero?
well, because, I mean, you still have that light parton in there too,
Okay.
which can have an, you know, which affects the momentum balance.
Okay, maybe I'll have to think about this because
Well,
I'm probably
I mean,
missing something obvious.
no, as you can see here in this plot, right? I've gone from 0 KT kick to about 0.25 GeV to 1.5 to 0.25 GeV squared to 1.5 GeV squared approximately. That's just how it happened to be at this particular energy. And so you still have kind of a back-to-back peak here, but then it goes down a bit more and a bit more as you increase this delta. So I mean, it does have a big effect on the charm distribution, much more than on the bottom, as you could already see. And here you see it even more so.
Okay. Anyway, are there any other questions? I don't see any other questions, so I would like to use this opportunity to thank Ramona for a detailed presentation of all of these results. Thank you.
Thank you, Igor. Thank you for inviting me.